Okay, so I'm going to try to teach you a little bit about infrared spectroscopy today. Hopefully this will help you in your organic or spectroscopy courses. So I'm going to skip through some of this. Some of this is for my more advanced class, but the basic idea is that a molecule has many different various vibrations, some movements represented by a 3n-6 ratio, where the n is the number of atoms within a structure, and these are the number of unique vibrations. IR spectroscopy seeks to detect these vibrations through the absorption of infrared rays and how these cause it to vibrate. There's various IR radiation ranges: near IR, mid IR, and far IR, but most organic vibrations will occur in the mid IR region, and so we'll focus mainly on there. Due to this very small range, we'll actually use wave numbers or reciprocal centimeters to represent the wavelength. This means our 25 to 2.5 micrometer wavelength ranges from between 400 and 4,000 reciprocal centimeters. Now, what's going to happen here is that the vibration is controlled by several things. One thing is a spring constant, which depends on the bond itself, and the second thing is the reduced mass, which is the two masses that are stretching on that spring. So the heavier the mass, essentially the more energy it's going to take to vibrate those springs. So what's going to happen here is we're going to shoot it with infrared spectroscopy, infrared radiation of a certain intensity, and we'll measure it versus standard and see how this is absorbed. Now, the strength of this bond and the amount of light that is absorbed depends on the strength of the bond and the mass that needs to be moved. And the amount of light of a given wave number absorbed relates directly to the change in the molecular dipole that will be brought upon by this vibration. So where it absorbs depends on its weight and the strength of a bond. So things like OH and C double bond O will have very strong absorptions. There is also going to be certain stretches we do not see because there will be no change in dipole, and so you'll see no absorption in the infrared energy, even though the molecule can vibrate. So certain stretches will be IR inactive. So just because we don't see a stretch does not guarantee the absence of a functional group. So we can see various different types of stretches: symmetrical stretches, asymmetrical stretches, bends, like twisting, wagging, rocking, scissoring type bends of how the molecules are moving. For the most part, we'll be looking mostly at symmetrical and asymmetrical stretches. Now I'm going to go ahead and skip through the instrumentation, but just know that there is many different ways we can work through this. The more important thing is looking at and interpreting the IR. So first thing to note is the 4,000 to 3,200 region. These are where you're going to see the OH and NH. These are typically broad, they're intense because of the electronegativity. The broadness is due to the hydrogen bonding. So if you were to do this in a very dilute solution or in the gas phase, it would become really sharp. Now, a primary nitrogen will see usually 2 NH stretches, but a secondary N will see only 1. And of course, a tertiary N will see 0 because we have no NHs. And another thing to note is OHs or NHs adjacent to a carbonyl, so such as a carboxylic acid or amide, we'll see a shift to a lower wave number. So so OHs typically range anywhere between 3300 to 2500, and NHs in that case would be 3350 to 3060. But so those are these two ranges, but basically you can see a hydrogen bonding molecule usually in this range. Now for carbon, you can almost always see a CH bond. The most common one you'll see is sp3 hybridized, which is 3000 to 2840. So 3000 to about 2850. One thing is 3000 is a nice sharp cutoff. Everything above 3000 is indicative of, say, a double or triple bond, a pi bond of some kind. So 3100 to 3000 is sp2 hybridized, and 3267 to 3333 would be sp hybridized. And of course, below the sp3 we have aldehydic stretches. These are a little bit different because of how the inductive effect of the aldehyde kind of weakens our CH bond, changes our CH bond. So, but either way, you only really see CH bonds in this region, so 3300 to 1700. So we don't really have to worry about anything else. I think I meant 2700, not 1700. Now, next thing is kind of by itself, 2300 to 2100. This is where we'll see our triple bonds. Our nitriles will be incredibly sharp and intense because of once again, the dipole moment. And alkynes, if they show up, will be weak to moderate intensity. Now, if the molecule is symmetrical around the alkyne, we will not see it. So, symmetrical internal alkyne will be IR inactive because there will be no dipole change. These guys, because they're linear, can only symmetrically stretch. There's no bending. So, but of course, if you have any carbon dioxide impurity, it would show up in this region as well. Now, the next thing to worry about is the double bonds. So, between 1850 and 1500, you could get various double bonds, including carbonyls, which are going to be very intense. But they can go from anywhere from 1850 to 1550, depending on inductive effects, hydrogen bonding, resonance, ring strain, all sorts of things. But they are really intense peaks. A double bond from carbon ranges from 1670 to 1600. But this can also be affected by resonance and ring strain, with aromatic being below that 1600 to 1550. And then imines, so C double bond N, strong peaks that'll show up from 1700 to 1600. One other type of peak that could show up here is also an NO stretch from a nitro group, which show up between 1550 and 1500. And finally, there's the fingerprint region between 1300 and 900. We almost always ignore this region because there's too much of a mess. In this region, you can often see a very strong CO or CN stretch, but it's often not worth the effort to try to pick it out. And of course, below 900, you might be able to see some strange aromatic bends, which if you're trying to determine the substitution of an aromatic pattern, it might be worthwhile to try to use this. But if you have NMR, you almost always want to use NMR. So anything, the fingerprint and below, is often not really worth the effort. And I'm going to skip these guys. We're not going to have to worry about those for the most part. But okay, let's look at some spectra and see what we can see. C6H12O. So this structure, both of these have 1 degree of unsaturation. So what can we tell here? I see in this region 3000. There is there's some mess. The 3000, 2900, 2800 CH-sp3 hybridized carbon. I see there's no OHs, and I see a strange stretch. This is about 2700. So that tells me something. Along with this, 1900, 1800, that's about 1850. This is a C double bond O stretch. Now what this tells me, this is a CH aldehydic stretch. So what do I have here is hexanol. The 6-membered aldehyde. Now, same C6, what do I see? 29, 28. There is no aldehydic CH stretch, and we're still at 1900, 1800, maybe closer to 1700, another really intense C double bond O. So instead, this tells me this is most likely a ketone. So we have some sort of hexanone. Whether this is 2-hexanone or 3-hexanone, that cannot be rightly determined by this alone. But we do know that, in both cases we have a carbonyl stretch, but in this case we have an internal stretch versus an external stretch. Now here, just looking at the difference between C4, so an alcohol, a butanol, versus a butylamine. In both these cases, we have the CH stretches, but in the alcohol version, we see this one single broad OH, while the NH version, we see a less intense but double humped stretch, suggesting that we have, this is the amine. Looking here, 1, 19, 18, 17, 16. These stretches are in the fingerprint region. We're not going to worry about them. Maybe one of these is from the CO, but not worth it. We got all we need in this to tell us, there's an OH, so of course there should be a CO. Now look at that C4H6. C4H6, okay. We have 2 degrees of unsaturation. 2 degrees of unsaturation. So, what do we see here? See a 3000, 30, 31, 32. That's about 3300. Right here, this looks like to be a alkyne, with that being there, and this little sharp peak at 2100 is the C triple bond C. Now, this is an external alkyne. We can tell that because we have a CH alkyne stretch and we have a C triple bond C. Now, C4H6 down here, this one, we don't see either of those features. We don't see the C triple on C stretch, and we don't see the CH stretch. So this one is an internal alkyne. It's really hard to tell what this is based on IR alone. So keep in mind, there's still a triple bond in there. It's just we do not see it by IR. So I just wanted to run through a couple of those quick examples. Hopefully that this will help you in the future.